Hello everyone. So this is Mallikarjun, working as assistant professor in Department of Flickr Link, Institute of Aeronautical Engineering. So today we are going to discuss about different types of DC generators. So with respect to previous classes, we have discussed about how the construction of DC generator will be, what are the different types of windings associated with it, and what is the amount of EMF generated. That is, we have calculated the expression for generated EMF in case of a DC generator. And in the today's class, we will discuss about the types of DC generator. So what are the different types of DC generators we have, and what is the representation of each and every DC generator. That is, if it is a series generator, how it has been designed, how it will be designed, what is field winding, what is armature. We will discuss about all those parameters with respect to different types of DC generators given here. So these are with respect to these types of DC generators has been classified depending upon the field winding. So I believe that the field winding is the main parameter which will play a major role. So depending upon the connection of that particular field winding with respect to generator circuit, this classification of these DC generators has been done. And depending upon the connection of field winding, the DC generators has been majorly classified into two types. One is separately excited DC generators, and the next one is self-excited DC generators. So depending upon what? Depending upon the connection of the field winding in the generator circuits, DC generators are majorly classified into two types. The first one is separately excited DC generator, and the second one is self-excited DC generator. So we will discuss about the each and every generator, what is separately excited DC generator and what is self-excited DC generator, and what are the types involved in it with respect to its circuit diagram. That is how the representation will be. So the first major type of DC generator is separately excited DC generator. You can see the figure which is mentioned in this particular slide here, where it gives you an idea about the design of a separately excited DC generator. So what is the meaning of separate excitation is nothing but the field winding will not be present with us in the generator circuit. It will be separated from the generator circuit, and the excitation will be given to the particular machine in order to run. So the best definition of this particular separated excited DC generator is a DC generator whose magnetic field winding is excited from an independent source of DC electric supply like battery. So if the excitation of that particular DC generator is done by means of an external source, like a battery or whatever it may be, other supply mode, a driven generator, hand driven generator or battery, then that type of generator is considered as what? Separately excited DC generator. That is, excitation to the field winding is done by using an external means. External means are nothing but what? A battery connected. And you can see the connection diagram of this particular separated DC excitation here. And you can see a GC. This is nothing but general representation of DC generator. These are nothing but brushes. And you can see here it is connected to the load. And the excitation to this particular DC generator is connected here. This is nothing but my field winding. And the field winding is separately connected to a circuit by using this particular DC. This is nothing but what? My battery. So this battery is connected to the field winding for the purpose of excitation by means of an external source. That is the reason it is called as a separately excited DC generator. That is, the battery will not be present, or it is either connected in series with the generator armature terminals, or else it will not be connected with the parallel with respect to generator armature. It is completely connected externally by means of an external source. That is nothing but a battery. And in case of this particular separately DC excited, the voltage generated completely depends upon the speed of armature rotation in field current. As we know that the expression for generated EMF in case of DC generator is 5Zn by 60 into P by A. And when I am concluding about this particular expression, I said that the value of this generated EMF completely depends upon two parameters. One is nothing but flux and the other is nothing but what? Speed. The same thing is mentioned here. The voltage which is generated in case of a separately excited DC generator also depends upon the rotation, that is nothing but which is indicated by N in terms of RPM or RMS, and the next one is nothing but what field current, or else it can also be called as a flux in case of a machine. Flux in case of a machine. With the speed increases, the greater the speed of the armature and field current, the greater is the induced EMF. We can see by this particular, if the speed is increased, if the flux produced increase, what about the induced EMF or generated EMF in case of DC generator, which also gets increased. If it is decreased, automatically the generated EMF in case of a DC generator will also get decreased. However, the separately excited DC generators are rarely used in practical applications because in order to excite the field winding which is present in this, we need an external source like a battery or some other power source which is used for the field excitation. So this is the major disadvantage, as it cannot be used in case of a practical applications when compared to self-excited DC generators. So what is the major disadvantage of this? We need an external source in the form of a battery in order to excite my field winding. So the whole machine cannot be connected directly here. A separated source is needed. That is the reason majorly separately excited DC generators are rarely used in practical applications. Rarely used in practical applications. Now we'll discuss about the next major type of DC generators, that is self-excited DC generators. Self-excited DC generators. So this type of generators whose magnetic field winding is excited from the output of generators, that is excitation of the field winding is done by the output of generator itself. So separate external source is not at all used in case of a self-excited DC generator, that is there is no use of battery, there is no use of any external power source to excite my field winding. In order to excite the field winding in case of this particular machine, I will use the output of the generator which is connected in the circuit. Suppose this is my generator. This is my generator. The output of this generator is used to excite this particular field winding, whether it is connected in series or else it is connected in parallel. So there is no need of connecting any external source like this, and for this I need a battery for exciting this as the of a separately excited DC generator here. The output of the DC generator which is in the form of EMF can be utilized in order to excite the field winding. Either the field winding may be connected in series or the field winding may be connected in parallel. Depending upon the manner in which the field winding is connected. So depending upon the connection of a field winding, if it is connected in series, that is called as a series DC generator. If the field winding is connected in parallel, then it is called as a shunt DC generator. If it is a combination of both series and shunt, then it is called as a compound DC generator. So depending upon what parameter in case self-excited DC generators has been divided into three types, depending upon the connection of field winding. If the field winding is connected in series, it is called as a DC series generator. If the field winding is connected in parallel, then it is called as a shunt DC generator. If the field winding is connected in both series as well as in shunt, then it is called as a compound DC generator. Compound DC generator. So we will go with the step-by-step procedure, that is what is series DC generator, what is shunt DC generator, what are the connection diagrams of it, and what are the expressions, mathematical expressions involved in this. What is shunt armature current, what is field current. We will discuss about all those expressions when we are discussing about this DC series generator, shunt generator as well as compound generator. Coming to the next slide. So first we will discuss about the series DC generator. So the connection diagram of series DC generator is given here, where the output, the field winding is connected in series with the generator armature terminals. So if the field winding of a particular machine is connected in series with the generator armature terminals, then it is called as a DC series generator. So always here the classification completely depends upon the connection of a field winding. If the field winding is connected in series with the generator armature terminals, then it is called as a DC series generator. You can see the connection diagram of this particular DC series generator here. This is the representation. The circle with respect to brushes gives you an idea about the generator here. And RA is nothing but an internal resistance. E is the generated EMF. IA is the armature current. IA is the armature current, and the field winding is connected here, where the resistance of the field winding, the field resistance is given as how much RSC, and the current flowing through the field winding is given as what? ISC. You can represent this as some RF and IF also, the nominations of yourself. And I have connected it to a load, where the current flowing through the load is given as IL. So by seeing the above circuit, as it is completely a series circuit, I can explain the relationship between the currents as IA equal to ISC equal to IL. That is, the armature current which is coming out of the generator terminals is equal to the current flowing in that particular field winding will be equal to the current flowing through the load, because all three terminals are connected in series. All three terminals are connected in series. That is, in case of a series, always the current flowing to the first point will be equal to the current flowing in the last point also. As these three, generator and field winding and load, are connected in series, the current flowing to the generator armature terminals, the current flowing to the field terminal, the current flowing to the load terminal, these three will be equal. That is, IA will be equal to ISC will be equal to IL. What is IA? Armature current. What is ISC? Field current. And what is IL? Load current. And what is IL? Load current. Load current. Now we will see the expression answer. Already we have come up with this particular expression. Always the value of current, armature current, will be equal to field current equal to load current. Why? Because all these three, either generator, armature, generator, or is the field winding or load, both are, as three parameters are connected in series, I can represent this particular equation. And in case of a DC generator, the field winding carries the whole load current. The field winding carries the whole load current. So whatever it may be the load current, it will carry the total. Thus, it is made up of a thick wire with few number of turns. Thick wire with few number of turns. So it possesses minimum resistance. So the field winding in case of this particular machine, that is DC series generator, should have a minimum resistance. Should have a minimum resistance, as it need to have a capacity to pass maximum amount of current. Maximum amount of current is nothing but what? Load current. So the field winding is designed with a larger thickness, which should have a minimum resistance in order to carry that particular amount of load current or maximum current which is flowing in that particular circuit. So this is what we need to. So this is nothing but what this gives you an idea about the design of a field winding. And the field winding which is present in the particular DC series generator carries whole load current or full load current or maximum current. The field winding thickness should be very large with few number of turns. So by designing in such particular manner, it possesses the minimum resistance. It possesses the minimum resistance. Already we know that from Ohm's law it is given as I equal to V by R. If that particular material or winding possesses less amount of resistance, what about the value of current? It has a high current carrying capacity. So based upon this particular proportionality equation, I equal to V by R, which is derived from the Ohm's law. So we need to design that particular field winding circuit in case of a DC generator. So as all these three parameters are connected in series, I can say that the expression for armature current will be always equal to field current, which will be in turn again it will be equal to the load current, where ISC is nothing but, we know that I already have said about the parameters in the circuit. ISC is nothing but field current and IL is the load current. And what about the value of terminal voltage? Terminal voltage is nothing but what? Load voltage. VT will be equal to E. VT will be equal to what? VT will be equal to E minus IA into RA plus RSC. IA into RA plus RSC. What is RA? Armature resistance. What is RSC? Field resistance. That is, if I want to calculate the value of terminal voltage which is present here, VT will be equal to generated EMF minus current flowing, total current flowing, that is armature current, into resistance offered by this particular circuit field winding plus internal resistance of armature, that is RSC, where RA is the armature resistance, RSC is the field resistance, IA is the armature current, E is the generated EMF, VT is the terminal voltage. VT is the terminal voltage. VT is the terminal voltage. So the points that we need to remember with respect to when we are drawing a connection diagram of a DC series generator is the series winding which you are keeping, it should be having maximum thickness so that it can carry maximum amount of current through it, which offers minimum amount of resistance, which offers minimum amount of resistance, which offers minimum amount of resistance. The winding which used in case of DC series generator should have a maximum amount of thickness to carry some high amount of current. Now we will discuss about the shunt generator. So if the field winding is connected in series with the generator armature terminals, it is called as a DC series generator. If the same field winding is connected in parallel with the generator armature terminals, it is called as a shunt DC generator. Suppose let me say that this is nothing but my generator. So this is nothing but my armature current IA, and resistance offered by this is the, and the output is nothing but induced EMF. If I connect the field winding in parallel with the generator armature terminals are nothing but A and A. It is represented like this in a particular practical representation. If this field winding is connected in parallel with the generator armature terminal, then this circuit is considered what? It is considered as a DC shunt generator. DC shunt generator. Shunt is nothing but it indicates the parallel connection of a field winding here. So this is the general connection diagram representation of a shunt DC generator, where the generator armature terminals is connected in parallel with the shunt generator and as well as load. So by using this, we need to derive the expression. You can see here IA is nothing but what? The current. IA is nothing but armature current. IL is load current. ISH is nothing but what? A shunt current, or else it can also be called as a shunt field current. Or else it cannot be called as a shunt field. By applying the KCL at this particular point, IA equal to, that is currents entering should be equal to currents leaving. So this is the relationship for the number of currents that are flowing in case of a DC generator. If it is a series, we have got this particular IA equal to IL equal to ISC as they are connected in series. But here they are connected in parallel. If it is connected in parallel, always the current division will take place from one particular point. So by applying a KCL at this particular point, the expression for a current in case of a DC shunt generator is given as IA equal to IL plus ISH. What is IL? Load current. What is ISH? Shunt current, or else it can also be called as a field current. And what is IA? Armature current. And what is IA? Armature current. Now by using this particular connection diagram, we will represent the expressions for the current and also the value of terminal voltage and generated EMF in case of a DC generator. Now, so we have used this particular equation by using what? By applying a KCL at that particular node. And the shunt field current, always the value of shunt field current ISH equal to V by RSH. That is nothing but terminal voltage. Terminal voltage, you can see as they are connected in parallel, the voltage across this will be equal to this particular point. Yes or not? Then what about the current flowing? ISH will be equal to terminal voltage VT and a resistance offered by this particular element, that is nothing but RSH. That is nothing but what? RSH. The same thing is illustrated here. And a terminal voltage VT. This, whatever the value of VT, I need to apply KVL in this particular loop. VT equal to E minus IA into RA. Yes or not? If we apply the KVL in this particular loop, by applying the KVL in this particular loop, KVL is nothing but what? The sum of voltage drops in a particular closed loop should be always equal to 0. Always equal to 0. Then the expression for terminal voltage is VET equal to E minus IA into RA. What is RA? Resistance offered by armature resistance. What is IA? Armature current. E generated EMF. VT terminal voltage here. So these are the different mathematical expressions that are evolved from the what? From the design of the connection diagram of a DC shunt generator. Design of the connection diagram of a DC shunt generator. So these are the different, you need to remember this particular circuit diagram and also the mathematical expressions which are evolved in the simple equations. There may be a chance of getting such model problem based upon calculate the armature current for a DC shunt generator or field current or terminal voltage or whatever it may be based upon this. Now we will discuss about the next important type of DC generator, that is compound DC generator. Compound DC generator. That is, compound is nothing but it is a mixture. It is a mixture. where it consists of two set of field windings. Up to now we have seen why, because this complete classification of DC generator has been done depending upon what? Depending upon the connection of a field winding. If the field winding is connected in series with respect to generator armature terminals, it is called as a series generator. If the same field winding is connected in parallel, it is called as a shunt generator. If the same field winding is connected in series as well as in parallel with the armature winding, then it is called as a compound generator. That is, in order to design or else in order to draw the connection diagram of a compound DC generator, I need to have two set of field windings. One should be connected in series and other should be connected in parallel with the armature winding. One should be connected in series with the armature winding and other should be connected in parallel with the armature winding. And this depending upon that particular connection, the compound DC generators has been classified into two types. Compound DC generators has been classified into two types. One is short shunt compound DC generator and the other one is long shunt compound DC generator. One is nothing but what? Short shunted DC compound generator and the other one is nothing but what? Long shunt compound DC generator. We will discuss about what is short shunt compound DC generator and also what is long shunt DC compound generator here. Now, a short shunt DC compound generator, as I have said earlier, it is a combination of what? It is combination of both series field winding and also the shunt field winding. So, if it is a compound generator, it need to have two field winding sets. One is connected in series and the other is connected in shunt. So, we can see here. So, if it is a short shunt compound generator, this is the representation of a connection diagram of a short shunt compound DC generator. So, how it is connected? You can see this is nothing but my generator armature terminals, where E is the generated EMF, RA is the internal resistance of an armature, and IA is the armature current. And the field winding, one field winding is connected in shunt, and the other field winding is connected in series, and this is connected to load. This is the connection diagram of connection of short shunt compound generator. Short shunt compound generator. And the mathematical expressions which are involved in this is nothing but apply KCL at this particular point, where the value of relationship between the currents is IA equal to IL plus ISE. IA equal to ISH plus ISC. What is ISH? Shunt current. What is ISC? Field current in connected in series. This is the field current which is connected in parallel. In a similar fashion, I can calculate here. You can see in this, the value of field current is always equal to the load current, as these two are connected in series. That is ISC equal to IL. That is the second relation I have here. And coming to the third one, if I want to calculate the shunt current, how to calculate the value of shunt current? Shunt current equal to total voltage plus this particular thing. As the voltage, the total voltage should be taken. This parallel voltage will be equal to this, and voltage across this will be VT plus ISC into RA. So the value of ISH equal to the total voltage across this particular branch, that is VTE plus ISC into RA by RC. So this is the expression which is used to calculate the value of shunt current. This is the expression which is used to calculate the value of what? Calculate the value of shunt current. Coming to the next expression, what is the value of terminal voltage? How to calculate the value of a terminal voltage here? So the expression for terminal voltage is given as what? It is given as E minus IA into RA minus ISC into RSC. So this is the equation which is obtained by applying KVL in this particular loop. If you apply KVL, the sum of voltage drop across each and every element should be made equal to 0. So how to calculate the value of VT should be equal to E minus IA into RA minus ISC into RSC is the expression for terminal voltage of a short shunt compound generator. Similarly, we need to go with the long shunt compound DC generator also. You can see here, previously in case of a short shunt KP generator, there are two set of windings. One is connected in series, other is connected in parallel. Both are field windings. As it is a compound generator, we need to have two set of field windings. One should be connected in series, other should be connected in parallel. So if the field windings are represented like this, it is called as a short shunt. In case of a long shunt, it is represented like this. So for this, what is the expression for currents? IA will be equal to ISC, or else the value of IA equal to ISC will be equal to IL plus ISH. What is IL? Load current. What is ISH? Shunt current. And what about the value of this particular ISH? ISH will be equal to this particular thing, voltage across this particular terminal by V by RHS. You can see the mathematical expression involved in it. VT by RSH, and the terminal voltage is printed like this. ISC will be equal to IA. RS it can also be written as ISC equal to IA equal to IL plus ISH. So these are the different mathematical expressions which are involved in explaining the connection diagram of this particular long shunt DC compound generator or short shunt DC compound generator. Short shunt DC compound generator. Short shunt DC compound generator. So how the classification of this particular generators has been done? The classification of DC generators can be done mainly based upon the connection of field winding. If the field winding is separated, if the excitation of field winding is done by an external means with the help of a battery, then that is called as a separately excited DC generator. If the field winding is connected in series with respect to generator armature terminals, then it is called as a DC series generator. If the same field winding is connected in parallel, then it is called as a DC shunt generator. If the same field, if you use two set of field windings, one connected in series and other connected in parallel, then it is called as a DC compound generator. And we have come across the different connection diagrams here, how they are connected, and what is RSC, what is IL. We have come across certain relationship between the different parameters which are involved in this connection diagrams also. So series generator, shunt generator, and also the compound generator, and the types of compound generator, which include short shunt compound DC generator and long shunt compound GC generator. The representation of this particular connection diagram of short shunt compound generator and also the long shunt compound DC generator is very, very important. Depending upon this, you need to derive the mathematical expressions here, and based upon this, there may be a chances of having certain problems here. So with this, I am concluding this particular topic. We'll meet in the next class and we will discuss about the other parameters.
Like, share and subscribe. Hit the bell icon for more updates.